Hi there, and welcome to another little chapter of enablement and training for Fiber Seeker 3. And welcome, Fiber Seekers. Today we're going to talk about fiber placement. This is a really important chapter to better understand how we are able to place fibers during printing and what they actually do. So let's get started. And this first picture also already shows a lot of things. So let's start with the upper left picture. What you can see here is how we are able to place fibers internally in a part. Kind of similar to infill, but we offer a lot of flexibility in order to do so. So you can adjust the geometry of this so-called lattice structures. You can also define the angles between, let's say, the XY and a triangle or the angle between triangles. You could also do full surface fiber printing, which is kind of, well, I won't do it. Anyways. So lattice structures are actually very good for distributing stresses inside parts kind of equally, but we can also do it in an isotropic way by simply defining the angles between those triangles. We can give lattice structures a certain direction. You may refer back to your engineering studies. We call this quite often lattice structures, or we call it also a sandwich profile, where you have a top and a bottom surface, and in between you have this lightweight structure, which still gives a lot of strength. On the upper right picture, you actually see different types of fiber placements. We are not only able to produce lattice structures, we can produce fibers on the circumference of a part, also around holes or cutouts, but we can also freely define fiber passes, and I will show this in more detail later. So a lot of examples that show you how to place fibers in parts and how this can be done, basically. So some of the basic properties of carbon fiber. The maximum strength of the carbon fiber is only in the fiber direction. You may easily break it, even if you push it together, it breaks easily. Lattice structures are used as, I would call them, stress distributors. But we also allow fiber placement only where needed, and I will come to this point later on. The advantages are obvious: maximize strength, minimize the amount of fiber, and with this minimize print time while producing super lightweight parts. So let's have a closer look at this representation. Unfortunately, on the left side, the stresses are shown instead of the stress vectors, which would be a clearer explanation for what we do. Assume this part gets bolted on the top two holes, and let's assume it gets pulled on this center hole down in the middle. So what would be the ideal way to place fibers inside this part? Well, the ideal way would be in the direction of the stress vectors occurring in this part. And it's actually not always needed to do a simulation to figure it out. Sometimes it's just about clear thinking and say, hey, if I do this, that would be a good thing to do. And what you also can see on the right side is that the fiber pathing is actually almost different from the part geometry. And let's see how we can do this. So in this part, we import a second solid, which we use as a mask. So we just import it and put it to a common center point. And after we have done this, you basically cannot see it anymore. But then we can give this second solid the attribute to be a mask for the first solid. And with this, we can give the mask basically different fiber routing properties than the rest of the part. So in a sense, the mask could define the fiber passing inside our part. This is very important because in a lot of cases, parts only need to be reinforced at a certain point. Maybe they get bolted onto something and you want to just reinforce this point. So you just add a second solid or some primitive geometries we have in our slicer and make sure, hey, fiber placement is restricted where needed. So in a sense, what we do is actually placing the fiber at the point of need. Again, reducing the amount of fiber needed, and again, reducing print time because the fiber process is slightly slower than the printing process of the matrix. So let's move forward. There are just a few competitors outside which use a different technology compared to our continuous fiber co-extrusion. Most other vendors use laminated fibers with a plastic impregnation. So what they basically do, they use nylon as a matrix material, and then they use a nylon impregnated fiber and basically iron it, heating it up and ironing it in the previously printed matrix layer. But this comes with a few restrictions. You can, for instance, just do the circumference of a part or around cutouts, or you can do full surface. There is no way to produce something like lattice structures, and there is no chance to use masks for very specific fiber placements. So there is a limitation coming from the technology. It's not meant to be a disadvantage, it is just a limitation, because nylon impregnated fibers only work with nylon as the base material. So you are limited to nylon only, and I'm a plastics engineer and I'm a firm believer there is a good reason for we have hundreds of types of plastics, which is that plastics have been developed with a purpose in mind. So basically, you should be free to choose the right material for the right technology. Now, thanks for watching, and if you want to have some additional fun, here is a little quiz you can take, because I think it's always a good idea after you have learned something to challenge yourself with a few questions. Grab your phone, scan the code, and compete like a pro. Thank you very much for watching and see you next time. Bye-bye.